Can everybody hear me in the back? All right. Welcome to algorithms. And let's get right to it. There's a 12-hole centrifuge. And everything is equally balanced. The holes are equally spaced in the middle. And the question is, can you test 5 test tubes? Can you spin up 5 test tubes at the same time and have it be still balanced? And when something is out of balance, it rotates quickly, it starts to vibrate, and shake, and possibly fail, so it's important it's perfectly balanced. So the question is yes or no, can 5 test tubes be balanced simultaneously in a 12-hole centrifuge? How many understand the question? All right, only a few hands, all right, I'll repeat it. How many know what a centrifuge is? Okay, it's got some holes for test tubes. Spins really, really fast, 60,000 RPM, typically 1,000 revolutions per second, not per minute, per second. And it creates high G forces, and it separates fluids and blood and plasma or whatever you put in the test tubes. Medical labs use it all the time when you do blood tests. And so the question is, if you put 12 test tubes in there, and they're assuming they're equally sized, equally weighted, equally massed, equal density, it'll spin perfectly solidly and equally balanced, and nothing will shake or vibrate. Right? It's like if you try to put a pair of sneakers in a washing machine, or even one sneaker in a washing machine, you know what will happen. On a spin cycle, it'll start vibrating. How do you understand that? Okay, we try to prevent that from happening. Okay, so obviously if you put 6 test tubes, every other space, that would work too. How many can see that? It would be perfectly balanced with 6 test tubes. 2 test tubes you can do, right? Opposite sides, it'll be perfectly balanced. How many can see that? All right. 5 is the question. How do you understand the question now? Okay. Let's take a quick poll. How many say it's not possible? 5, there's no way to balance the test tube, centrifuge with 5 test tubes. All right, a few votes, that's good. How many say it is possible? All right, a few votes on the other side. And the rest of you are still thinking, which is good. That's good to think. Any questions so far about the question or the scenario? How many understand the question? Not the answer, the question. Okay, good. Any questions about the question? Because we'll come back to it before the end of this lecture. Talk about a few other things, and then we'll come back to this. And you'll see why I'm presenting it right up front right away. So far, so good? I'm beginning to realize lectures here will be pretty interactive. Yeah?
Does it matter what's inside them?
Good question. She's asking, does it matter what's inside them? Well, let's just assume that all the test tubes are the same size, same mass, same shape, completely identical, indistinguishable from one another. So there's nothing magic about one test tube that's not exactly the same about all the other test tubes. And each hole can accommodate one test tube and one test tube only. You can't double them up inside one of these locations around the periphery. So there's no tricks here. I'll never ask you a dirty trick question. And every question will use logic and sound scientific principles and rationale to answer it. And you'll be wiser every time you answer one of these questions or see it answered, even if you couldn't get it yourself. That's one of the main goals of this course, is to make you better problem solvers, better thinkers, quicker on your feet. This will also help you get jobs at Google and Facebook and Tesla and whatever your favorite company is. Because during interviews, they ask you these kind of questions. How many have seen interviews where they ask you kind of algorithmic or problem-solving kind of questions? Yeah, and if you can't answer enough of them, too bad, there goes your 6-figure job out the window. You can still program device drivers for IBM, but I wouldn't inflict that on anybody. Okay, any other questions about this riddle or puzzle problem? All right, so think about it in background while we talk about some other things. But try to come up with some generalized approach to addressing this. Think about what would work, what would fail, why, and try to get some lessons out of it. And we'll do that before the lecture is over. But again, it's no tricks, equally spaced holes, like the hours on the clock, identical test tubes. And by the way, you don't have to be test tubes, it can be any object you want. Right? Okay, so this is a course on algorithms. And it assumes some background of discrete math, but not too much. Everything will be done from first principles. This will be the book we're using, Corman, 3rd edition. And it's by a bunch of professors from MIT and elsewhere, and it's a very good book. And the reason I know it's a very good book is on the back cover, these reviews says it's a very good book. In particular, one of them says it very, very strongly, and it's by me, so I how many have already obtained this book? It's good. I highly recommend it. You can buy it used. There's also a PDF searchable copy of it on the Colab site. But again, please respect copyright laws. If you find it useful, please buy your own copy. But for your information, there's a searchable copy. It's nice to have a searchable copy of any book because you can search for stuff very quickly instead of just perusing it for hours, not finding exactly what you need. Okay, so there's also supplementary readings that I'll ask you to do in this course. And one of them is How to Solve It. I want you to all read this book. How many have read this book by Polyak called How to Solve It? It's a classic. It's an oldie but goodie. It's written a long time ago, but it's still very, very, very valid today. Nothing in it aged, really. It's general problem solving, how to think rationally and systematically and scientifically and solve problems and get them solved. So you'll all be reading that for fun and extra credit. There's also articles and videos on the class website. By the way, everything is on the website. The slides are on the website. I'm recording the lecture 2 different ways. Those will be on the website. All the handouts, everything will be on the website. And there's also a Colab site that will mirror some of that, but we'll use the website first and foremost. So that's the book, and that's the kind of secondary book, How to Solve It. And we'll go through history of algorithms, we'll go through lots of problem solving, we'll cover some of these topics as time permits, most of these really, on this slide, all of them. There's a long list of topics involving algorithms and even data structures. We'll go through that. I'll assume some background, but not too much. I'll assume you have some discrete math background, you know what a graph is, and nodes are, and edges, and that kind of thing. You know what a tree is and a hash table. But we'll also go over it from first principles. We'll just go over it more quickly than we would in an undergraduate course, because I don't want to leave anybody behind. But I don't want to waste too much time on things that are very fundamental, too simple, but rather focus on the underpinnings, the fundamentals of what's going on, kind of at the bottom, and the subtleties and the more clever stuff rather than just the mundane stuff. So we'll go through some sorting and searching. I'm sure you've seen sorting algorithms before, and I'll show you some interesting Jedi tricks about sorting that you may not have seen before. And we'll talk about finding min and the max and the kth largest. That's called selection. How to do that efficiently, particularly in linear time. That's not easy to do at all. Detecting majority elements, meta-heuristics. We're going to get into computational geometry in the second half of the course. Talk about convex hull and Voronoi diagrams and nearest neighbors and all that good stuff. So this you probably have not seen before even at all at the undergraduate level. That's really cool stuff. Again, everything is algorithmic, but when I say that, when I say everything, I mean everything. You get up in the morning, you start running algorithms. You're brushing your teeth, taking a shower, getting to your car, driving. Driving is a complex algorithm. Now there's cars that can drive themselves, and it's all algorithms. It's algorithms on wheels. The Tesla Model S can do 0 to 60 in 2.3 seconds. That's really cool, algorithms on wheels. So we'll talk about graph algorithms later in the course. We'll talk about depth first search, minimum spanning trees, Steiner trees, radius cost trade-offs, and this will be kind of graph algorithmic centric, things about graphs and how you compute things related to graphs and various properties of graphs. And then we'll get into entry completeness, and that's a whole theory of approximation and feasibility. What can be done efficiently and what can't be done efficiently and why, and how lots of problems are related to one another. and they can all be reduced to one another, so together they fall, together they stand in terms of algorithmic feasibility, and it's a very, very illuminating, very important kind of pillar of computer science. How many heard of NP-completeness before? Okay. How many could do an NP-completeness reduction? Okay, fewer than heard about. That's okay, we'll do that here, that's why we're here. So, other things that we'll cover as time permits includes other kinds of algorithms, network flows, distributed algorithms, how do you compute stuff when you have different nodes in an asynchronous environment and don't have a global clock. It turns out things become much more complicated than so. And it's much harder to do things. We'll talk about amortized analysis, zero knowledge proofs, and a few other things. But we'll keep the big picture in mind. You know, really it's all about problem solving. And problem solving is a very general human endeavor. All of us do it every single day, every hour, every minute of our existence. We're solving problems, running algorithms in our heads, adapting, learning, refining our ability to do that. And the more adept you are at problem solving, the better off you are, the better off all of us are, the human species is, and the less problems we get into as a society, as a species, as individuals. And it's problem solving is probably the number one most important thing that you can get good at. And it's very, very impactful on everything else that you do. All right, and don't forget always this another alternate motive is to have fun, to enjoy what you do, to do cool things, to learn stuff. Never underestimate that, that's important. And we'll try to do that too. So a brief history of computing. A lot of people came before the current era and contributed to what now we call computer science. It started with the ancient Greeks. In fact, the ancient Greeks had a computer already. It was a mechanical computer. It was 2,000 years before electricity was invented, but it was mechanical and it worked. We'll talk more about that in a second. And then, of course, Aristotle, Euclid, Archimedes, all these contributed. The people I'm highlighting in red here contributed more than the others towards our field of computer science, but they all contributed. So Boole invented Boolean logic, and Morgan popularized Boolean logic and made it more sophisticated and systematic. Basically, these guys showed that you only need two numbers to compute, 0 and 1. Before that, we had no idea that those two numbers are enough. So you need more numbers, and they'll name those large numbers and so on, but zeros and ones suffice. I'm not saying it's convenient or fun or even efficient to count with only zeros and ones. The point is, it's possible. And machines can do it, and once machines can do it, they can do it a billion times faster than humans, and then we all have iPhones in our pockets before too long. But it goes back to these people who showed what's feasible, what these machines can do, and that they can do it much faster than humans. And Cantor and Hilbert and Russell kept pushing on discrete math and all sorts of other interesting concepts. And then later, Church and Turing. Church was Turing's advisor at Princeton University back in the 30s. And Alan Turing, you heard about him. How many saw the Imitation Game about Turing? Yeah, so that kind of tells you the story about how he did at least one of his contributions to breaking the Enigma cipher, German code, which enabled the Allies to finish World War II much faster than otherwise was possible. So he basically saved millions of lives by doing that. And that was only one of a dozen different major contributions that he did. He also invented neural nets upon which all machine learning now is based. And he did 10 other things that are just as impactful and important. Von Neumann, Klein, and Chomsky, we learn more about these guys. This was a theory course. We'll dive deeper into all of their contributions. But they too contributed much towards algorithms and computer science in general. So here's this ancient computer I mentioned. It's called the Antikythera. It's the oldest known mechanical computer. We didn't even know about this until just a few years ago, back in the 90s. Somebody discovered it as in a fossilized stone underwater somewhere, and it was all kind of grungy looking. And basically it computed eclipses and astronomical positions of various heavenly bodies, and it was very, very sophisticated for its era. Remember, this is roughly 200 BC. This was constructed. 2,000 years before electricity was even invented. So it's not Babbage that created the first computer, it's really the Greeks. And we didn't even know that. And that's what it looked like if it wasn't fossilized. We kind of recreated it from the fossils and using X-rays to see what's inside these stones and these parts. And it's still the subject of much research. How many heard about this ancient computer, 2,000-year-old machine? Yeah, just one. So this is the precursor to your smartphones, people. This deserves a lot of respect and street cred for doing computations and doing them 2,000 years ago, mechanically. And these are other pictures of the replication of it and the simulation of it. And they build models, and it works beautifully once you put it together in a nice way from the blueprints. And it even had its own manual that was written in Greek, how to use it, and it was equivalent of a Swiss watch, But even though it was 2,000 years ago, and most people just had stone tools, and most people didn't even have that back then, that was extremely impressive. So computation goes back a long way, and algorithms. One of the articles on the website is about this machine. So this is actually pictures from the article, and I'm asking you to read it for extra credit. We'll talk more about extra credit in a second. So the prerequisites simply are some discrete math background, and if you don't have much discrete math background, that's okay. You can catch up, but you'll have to do it quickly so things won't get away from you. So this course will bootstrap from first principles, but the simple stuff will go through quickly. But it's all going to be there. The most important thing you should bring to the table is tenacity, is don't give up. Right? Even if you can't solve a problem in half an hour or an hour or even a day, don't give up. Sometimes some problems will take a week or a month. I'm not saying you should work it on a week, like 12 hours a day for a whole week. No, just work on it for a few minutes, go away, do other things, come back the next day, work on it for another 5-10 minutes. And after about a week or 2 weeks of doing that, kind of coming back to that, all of a sudden the insight will occur to you. You'll have some eureka moment, like you'll be taking a shower or playing some sport, then all of a sudden you'll realize the solution of that problem that you've been thinking about on and off for a week or two. How many had this insight, this kind of revelation in the past with other courses or other material? Sometimes your brain works in background. Okay, so make sure you're enabled to work for your brain to work in background, kind of even subconsciously, by looking at the problems, thinking about the problems, and then going off and doing other things. And amazingly, you'll see that things become easier over time, even if you don't think about it continuously. So leverage that amazing ability of the human brain to solve stuff in background, almost in the subconscious level. Okay, but that means you gotta stay on top of things and read ahead, and not procrastinate and save things for the last moment before you even look at them for the first time. That's a killer. If you do that, you will not be very effective in almost anything you do in life. Don't procrastinate. You can't stress that enough. And we'll talk more about that. So exams, I'm willing to do in-class exam or take-home exam. We'll have a vote shortly before the exam time to see if you want to take it home or do it in class. I'm a big proponent of the democratic system, so I'm big on votes. Solve lots of problems, working groups, form study groups, right? 3, 4 of you, 5 of you at a time, meet every week or even twice a week, order pizza delivered or whatever your favorite catered food is, and solve problems from the problem sets. The problem sets are already on the website. There's already hundreds and hundreds of algorithmic problems posted on the website. How many have seen that? Okay. Those that looked at it, I'm impressed, because we did it before class even started. Those that don't have procrastinated a little bit already. But that's okay. We'll try to wean you off that nasty habit of procrastination. So the problem sets are not formally graded, but do them anyway, because look at this red line here, very emphasized that many exam questions, midterm and final questions, will come straight from these problem sets. And I'm not going to tell you which ones ahead of time, obviously. But if you solve lots of problems from these sets, when you come to the midterm or the final, you just write down the answers and walk away, because you've already solved them. If you don't solve them ahead of time, and you come to the midterm and the final, never having to look at those problems, you will have a very bad day. And again, I can't stress that enough. Problem solving is not something you can cram for. You can't cram for becoming a MacGyver over one weekend, right? Other things you can cram for. You know, if you want to learn the history of World War II, maybe in a weekend you could knock it out by, doing 20 hours of reading, and then you'll know all about World War II. But if you want to become a better problem solver, that won't happen in a weekend, or even in a month, or even in a year. It's a lifelong process. So you gotta do it systematically, tenaciously, relentlessly. Okay, so and procrastination is the opposite of that. So I can't emphasize that enough. All right, there'll be a project also that you can do, and extra credit problems, there'll be plenty of them. In fact, you know what, let's have an extra credit problem right now. Remember that centrifuge problem? Let's make that worth an extra credit point. If you can solve that before I actually give you the solution in about 45 minutes, extra credit to you. Write it down, write your name, pass it forward. So already there's one extra credit problem with an open bounty on it, even as we speak. There'll be many more. If you find mistakes in my slides, in my handouts, that's worth an extra credit. Let me know, email me what the mistake is, the glitch, the typo. I will try to fix it. Hopefully there won't be too many of those, because I pride myself on being correct and accurate and precise. I admire precision. I try to do that myself as much as I can, but when I fail, I will credit you for detecting my glitch. And you'll be helping me, you'll be teaching me at that point. Okay, so any questions so far about any of that? It's interesting, now that I said it's worth extra credit, the centrifuge, all of a sudden a bunch of people are working on it. So, okay, that's why I give it extra credit. If I ask you to do it for free, you may not want to do it. For credit, you will do it, that's good. That means capitalism works. Okay. Attendance will be worth 10%. I'll give you 10% credit just for showing up. How's that for a freebie? Like Woody Allen once famously said, 90% of success is just showing up, just being there. If you miss lectures, there'll be lots of stuff that's happening in lectures that you won't find anywhere else. You won't find it, in the book or in the notes or even in the slides. Those readings I mentioned will be about 20%, the midterm and the final about 20% each, so equal weights of these things. Projects will be about 30% because it'll probably take longer to do the project than the midterm and the final, but it'll be a programming project to implement some algorithmic aspects of some stuff we learn, or even stuff that we won't learn in this class if you want to kind of run off and on some tangent and learn more about some algorithmic subfield or area or applications. Be my guest, and I'll give you credit for that, and that'll be a good thing. And that will also involve a demo at the end of the semester. So again, the best strategy is to solve lots of problems and do lots of extra credit readings. And if you do all that, there's no reason why all of you can't get an A+. Okay? All right. I hate to talk about this topic, but it happens every semester. So cheating. Bottom line is, don't do it. It's bad. Cheating is bad. It's not good. You can get expelled. There's an honor code at UVA, and in recent years, cheating has become more and more of an issue because you can look stuff on the web, and there's even websites that enable cheating and support cheating. Just don't do that. You can work in groups and you can help each other and solve problems together. That's good. I encourage that. But solving problems together, working in a group, is not the same as one person solves it and 4 people copy that answer. No, that's not working as a group. That's just copying from another person without even knowing, what you're copying potentially. And even if you know what you're copying, you didn't do it yourself, so you didn't become a better problem solver. You're just a cut and paster at that point. And that's not learning. That's not good. That's not encouraging. That's not the point of us being here. And that's also cheating. So please don't just cut and paste and copy from people without putting in a lot of work yourself. It doesn't mean you have to come up with everything by yourself. You can work in groups and collaborate. It's all good. Everything is collaborative nowadays. Very few people work in isolation in the real world or even in research. Everything is collaborative. So I encourage that, but don't take advantage of it in a way that basically disables you, right? As well as being cheating. So don't just copy stuff. Work at it. If somebody else gets it while the whole group works on it, one person has an insight and everybody else builds on it, that's great. And you all got the answer together. Some people contributed more, some less, but nobody just got a free ride and just copied other answers without even trying. That's not good. And by the way, trying is very important. Even if you don't get the right answer, but you thought about it for hours and days, and worked really hard, and somebody else got the answer, and you said, oh, okay, impressive. You still got a lot of benefit from trying, because you tried a lot of things that didn't work, and you're better off for that. There was a lot of learning involved in that, even though you didn't get the right answer. How do you understand that? It's very important to remember that for two reasons. One is because you need to do a lot of that to get better. Try a lot of things that won't work. And secondly, you need to know that because that way you won't get discouraged when you work for long hours and even days, and you won't feel down. You won't feel like you failed. You feel like you succeeded in finding hundreds of things that didn't work. That's success mode. Right? Think about the subtlety of that insight. Thomas Edison said when he tried to invent the light bulb and nothing that they tried worked, he said, I did not fail. I succeeded in finding 10,000 things that didn't work. How many heard that before? This kind of sentiment. Just keep that in mind as you work on problems. Trying and not getting the answer is very, very healthy, very good. It wires your brain in the correct direction. Okay, so it's not about answers so much as about trying to get answers. In fact, that's what science is all about, is trying to get answers and trying to get better answers, even if you have some answers. Okay, so don't get discouraged. And, there's more details about cheating in the syllabus, but, don't do any of these things. Mass copying and looking things up without working on them. And, so I'm not saying you shouldn't look anything up, and you should. You should look at wiki pages, and you should look at other books besides the book that we're using. That's okay. In fact, the Colab site has a lot of books on it, as you'll see in the resource section. But plagiarism is pretty easy to catch these days. Some people think they're clever by going through your Google search, getting some answer, copying and pasting it into your homework or into your exam. But the TAs and I can also Google what you wrote and see exactly where it came from. Google works both ways. You didn't think about that before. You can find some answer, but I can find where your answer came from, just as easily as you found the answer. So, in fact, it's easier. All right, so don't want to harp too much on it. So I encourage collaboration very strongly. Just don't abuse that privilege. All right, so my contact information is here, and we'll have a few TAs. In fact, we have a couple of. Where are the TAs? Could the TAs get up and just say a few, 30-second introduction about yourself, your name and your interests? And
I'm William. I'm a first-year grad student in physics class. I also like algorithms, I guess.
all right, and there's another TA. Are they here? Okay. Anyway, yeah, just a few. Your name and a couple of things about yourself. Okay. Yeah, and there's a third TA that's will be around soon enough, and we'll have a schedule on the class website showing exactly what their office hours are, where they are, where you can find them. We'll have a staggered set of office hours that's basically every day of the week, including weekends. So 7 days a week there'll be a TA at some point, somewhere, waiting to help you, and the big calendar on the class website will tell you exactly where to find them and what hours they'll be around. And their schedule will be staggered on a half-hour schedule. In other words, they won't start like 2 to 3, they'll be like 2:30 to 3:30. Why is that a good algorithm for scheduling a TA? On a half-hour mark, not on the hour mark. Anybody think of a reason? It's more optimal. Why? That's not a hard algorithm question. It's a simple optimization. But let's see if you can understand why I'm doing that. Yes. Oh, thank you. So again, the question is, why should you schedule a TA hour on a half-hour mark boundaries, like 2:30 to 3:30, not 2 to 3 or 3 to 4? Yeah.
Is it easier just because most things usually run from like 2 to 3?
Yeah.
So somebody else can.
Exactly. Good. I should give you extra credit for that. Most classes run on the hour marks, 2 to 3, 3 to 4. So if a TA has a scheduled 2 to 3 time slot for the TA office hour, those that have a 2 to 3 class can never see that TA. But if it's 2:30 to 3:30, those that have a 2 to 3 class can see them for the second half hour of their office. And those that have a 3 to 4 class consider for the first half hour. How many understand that algorithm or strategy? Okay, good. So we'll just do that. It's easy to do. Right? Easy, everything else I'll do with you. And of course, you can reach us by email, and if you need a special appointment, you can do that too. So the goal about the readings is to give you a very broad exposure to a lot of cool ideas that will expand your mind. And there'll be very diverse kinds of reading, but again, keep in mind that everything is in support of problem solving and making you a better problem solver, more effective scientific thinker. So there'll be about 20 items over the semester that we'll be doing. Remember, that's worth 20% of the grade. Those items are either TED Talks or short papers from Scientific American, or just websites that you go in and look around and learn some stuff. So there'll be diverse categories. And of course, you can do more than 20, and that'll count towards extra credit. Remember that percentages a few slides ago when I showed how much things are worth? There was one last category of extra credit, and that's worth at least 10%. So you can get a lot more than 100%. And if you don't do so much, as well as you thought on the midterm or the final, you can get lots of extra credit, and that will more than make up for the difference. So I want to make it easy for people to get all A pluses. Okay. Please help me help you do that. Okay, and that means you just need to stay on top of things, solve lots of problems, and do all the right things. But I'm not looking to stumble anybody. I like to give good grades, but you need to help me make that possible. So lots of extra credit opportunities. And here's an interesting heuristic. I want you to do at least 2 per week, because in some past semesters when we didn't have this rule, the last day of the semester somebody would submit all 20. Stay up 3 nights and look at, listen to 20 TED Talks and read 20 papers, and only one night or 2 nights, and that's not credible. And that runs afoul of the notion of problem solving and being systematic and relentless, and that's it's kind of pathological. Don't do that, and I'm prohibiting you from doing that by saying you have to submit at least 2 a week, otherwise you're late, and there'll be late points deducted. So nobody should lose points that way. So be sustained and systematic and relentless, and this is not very onerous. Again, a lot of these items are TED Talks or short 5-6 page papers and things like that. And all you got to do is tell me what you learned from them. I don't expect you to, analyze it ad nauseum or write a treatise about any of these. Give me a couple of paragraphs on each. If it's a book, give me a couple of pages on it, and also there's a minimum of 2 a week, and there's a maximum of 2 per day. So again, because I don't want you to wait till the last week of the semester and then submit 20 or 30, 40 things. Again, that would run afoul of everything we just said. There's no procrastination. And there's an email address that me and the TAs all have access to, and everything will accumulate there. So when you submit stuff, just email the attachment or the paper or the email or whatever it is to that email address. And all these instructions also are on the syllabus as well as on the slides. All right, so I want you to watch one video right away. And it's about time management by Randy Pausch. He was a friend of mine. How many heard of Randy Pausch, the last lecture guy? He died of pancreatic cancer in 2008 or so. He gives very, very good advice on time management. That's him giving the lecture in Cabell Hall, standing room only, almost 1,000 people showed up. Very practical advice about time management. And so of all the things that I'd like you to read specifically or watch, this is number 1. Not surprisingly, right? If you need to look at 20 different papers and videos on various topics, and one of them is about time management, obviously do that first, right? Because that will teach you how to do the rest more effectively and how to just be more effective in general in life by managing your time better. And it's very practical advice. It's only an hour long. If you think you don't have an hour to watch a time management lecture, you need to watch it twice. Okay? And I hope you can see the irony in that. And I'm not kidding, by the way. Another couple of things. The last lecture is just very inspirational. It's just a nice attitude towards life, very positive, no whining. This is a guy who had only a few months left to live, stage 3 or 4 pancreatic cancer. It's amazing what he did in the last few months of his life. So you haven't seen that lecture before, you should. When he wrote the book that accompanied the lecture, Disney paid him $7 million in advance just to start writing. Very, very interesting and powerful advice in that book, and it was worth every penny. It sold tens of millions of copies. Powers of 10 gives you kind of an idea of the scale of the universe in an interesting way that you may not have conceived before. And it's so interesting, I'll give you a view of it right now. So this is zooming in on scale. So that's a hummingbird, a mouse, and this is the scale, 10 to the minus 1 meters, so that's 10 centimeters. Now we're getting into coffee beans and ants, a millimeter across, 10 to the minus 2 centimeters. Bacterias, there's insects, amoebas, right? The human hair width right there, the wavelengths of light, nuclei, here's a chromosome, right? E. coli. So we're zooming in on scale smaller and smaller. The scale is down here in the corner in terms of meters. Here's a transistor, smaller than a virus, actually. There's a billion of them in every iPhone or smartphone in your pocket. DNA strand, right now we're 10 to the minus 8 meters. Buckyballs, nanotubes, right? Molecules of glucose, and then there's a single carbon atom, it's 10 to the minus 10 meters. And then we get into particles. There's a lot of empty space there before we even get to nucleus of an atom. Most of an atom is empty space, 99.9999% empty. Right, there's a helium nucleus, 10 to the minus 14 meters. And now we're at the femtometer range, and lengths smaller than 10 to the minus 16. We don't even know that they even exist in any real sense. Right? The space and time could be discrete, actually. There are some quarks, and that's about it for the lower end of the scale. There's some quarks are bigger than others in terms of radius as far as we know. We still don't know a lot about these things. Right? Electricity was just invented a couple of centuries ago, less than that. Now we zoom back out. So this is one of the readings that I'm asking you to do. So it's so cool and important. I'm actually having you do it right now in real time. But look at it again more leisurely. By the way, if you click on any one of these things, it tells you more about that object. It gives you wiki pages to it. And so now we're zooming out. So we see elephants and dinosaurs and houses and whales and giant sequoia trees and large airplanes. There's a Statue of Liberty. Now we're at 10 to the 2, so that's 100 meters across. There's the Titanic, the Great Pyramids, Hoover Dam, possibly one of the largest things ever constructed by mass. China Wall is longer, but I don't know if it's as massive as the Hoover Dam. Probably is. Mount Everest, some satellites of the solar systems are here, some states. There's California, there's Italy. Pluto is as small as some of the, smaller than some of the larger satellites, actually, like Titan and Ganymede. That's why it's no longer a planet. There's the Earth. There's the Minecraft world. Turns out much bigger than the Earth. So it's a Minecraft. That puts in perspective how large that world is. There's the sun. There's other stars besides the sun. Look how small the sun is compared to these other stars. In fact, if you take some of these other stars and put them where our sun is right now, we'd be inside that star. It'll go past the orbit of the Earth, past the orbit of Mars, into the orbit of Jupiter, actually. The sun is no longer visible, it's a little dot, and these other stars are orders of magnitude larger. Right? That's the distance of Voyager 1 from the Earth right now, several light days. And then we're still zooming out. There's other larger objects in the universe. We haven't even seen the Milky Way yet. Right? That's the distance to the nearest star right here, 4 light years across. That's a light year. And there's some nebula and some smaller galaxies beginning to show up. So now we're talking about 10 to the 17 here meters, hundreds of light years, thousands of light years, right? And there's some of the larger nebula, and soon we'll see the Milky Way itself, which is 100,000 light years across. And there's the Magellanic Clouds, that's tens of thousands of light years across. And there's some small galaxies, Triangulum Galaxy, Sombrero Galaxy. There's the Milky Way right there. That's 100,000 light years across. Right? there were cavemen on this planet before the light from the center of the galaxy reached our Earth. That's how big. And then there's bigger galaxies yet, and bigger objects, and clusters of galaxies, and the universe is a really big place. So when you see that kind of stuff, you know, you're beginning to wonder about, you know, all sorts of interesting issues. And you know, if you think all this was created just for us, it's a big waste of real estate. You know, we don't need all that space. We'll never see any of that space. And that's the observable universe, roughly 10 to the 25 meters, about 14 million light years across. Now we're zooming back to the human level, where you see animals and humans and people and so on. So anyway, how many have seen this kind of video before? Okay, it's really cool. And if you start clicking on these things on the actual app, you learn a lot more about these things. So this puts things in perspective. And you know, why am I showing you this? Well, besides expanding your mind and being really cool and interesting and makes you the life of your next party, orders of magnitude are very, very important in algorithms and in computer science in general, right? So, you know, if you hear numbers, you should be able to put it in perspective in terms of computer science terms, orders of magnitude. So if I say 2 to the 30, how big is 2 to the 30? How big is that? How many say a million? How many say a billion? How many say a trillion? Well, which one, roughly? A million, a billion, a trillion, quadrillion? 2 to the 30. How many say a billion? Why don't I see a sea of hands rising? 90% of you should name the right thing, right? You're a computer scientist. Everything is about powers of 2. Building construction systems, algorithms, databases, clouds, apps. And if you can't wrap your mind around powers of 2 instantly, you won't be very effective in your thinking and problem solving, even about algorithms and codes and running time and transistor counts and millisecond delays across networks. It's all about powers of 2. It's all about orders of magnitude, right? So don't feel too bad. You know, we have exactly the same situation every semester. But next time I ask you, what's 2 to the 30? You should say it's about a billion right away. Why? Because 2 to the 10 is 1,000, right? 1,024 to be precise. 2 to the 30 is 2 to the 10 cubed. So it's like 1,000 times 1,000 times 1,000. So 1,000 times 1,000 takes you to a million. A million times 1,000 takes you to a billion, roughly. And I'm not asking for exact numbers here. I'm just want you to understand orders of magnitude, right? If you don't know that 2 to the 30 is a billion, you'll probably never be a billionaire. just saying. Never mind 2 to the 20, which is a million. Right? So I don't want to depress you. I just want to get you excited and motivated and mobilized to just wrap your mind around these concepts and understand why we're harping on them, and then be very comfortable with them, right? So 2 to the 30 is a billion, 2 to the 40 is a trillion, that's terabytes or terabits or whatever, that's a trillion. What's beyond a terabyte? What's the next named number beyond that? Petabyte. And then next? Exabyte. And then? So I'll let you think about that, but if you're not comfortable with these numbers, you won't be very effective reasoning about these numbers and reasoning about things that have to do with these numbers. And nowadays, everything has to do with these numbers, right? Google has a cloud warehouse full of disks, millions of disks, that stores about an exabyte. An exabyte really costs about $1 billion and it's the size of a warehouse. And it draws about 1 million watts of power, actually several million watts of power, including the air conditioning. Every time you upload photos to the cloud, it's going into some storage space that's about an exabyte large. What about on the downside? A millisecond is how fast? What portion of a second is a millisecond?
-3.
-3, it's a thousandth of a second. Microsecond,
-6.
-6, it's a million. Nanosecond,
-9.
okay, what's next? Beyond the nanosecond. Picosecond, how quick is that?
-12.
-12, it's a billion Beyond picosecond, we got what? Femtosecond next. Attosecond. So not a lot. I don't hear a lot of voices on that. So, but understand your powers of two, and just generally orders of magnitude. It'll help you wrap your mind around more interesting concepts, more effective concepts, problem-solving techniques, and make you a much better problem solver. There's one company that's very, very good about thinking big, and they named themselves after a very large number. Google. How big is a Google? How many orders of magnitude is that? How many zeros? 100. So they named themselves 10 to the 100. That's our name. Why? Because they think big. They wrap their mind around very large concepts, very large scalable sizes. And there's a reason why they're the most valuable company in the world. Sometimes they flip with Apple in any given stock market thing. But still, because they think big. In fact, everything they do is so scalable, they couldn't use the normal operating systems like Microsoft, Windows, or even normal Linux. They have to write their own operating systems. They have to write their own databases. They have to create their own way of managing data in their cloud. Everything from first principles, everything in a super scalable way that never runs out. Never runs out of address space or storage or any of the other resources that you need to grow and grow and grow beyond bounds. Think about that. There's a reason why they're so successful, and it's right there in their name. So that's why I'm having you look at videos like this. It's subtle. Wax on, wax off. Okay. All right. This covers 50 orders of magnitude, from 10 to the minus 24 to 10 to the 26, and roughly we're right in the middle. This human scale that we are, 6 feet high, and these buildings and our cars and our pets are right there in the middle of 50 orders of magnitude, about 25 orders of magnitude in every direction, in each direction, up and down, high and low. So it's interesting. Other required readings, again, we'll just breeze through some of this, but there's something about Shannon being the father of an information age. I want you to watch that video, The Pattern Behind Self-Deception. This guy is a very interesting fellow that runs a journal called The Skeptic, and it teaches you how to not believe fake news, basically. And not just about politics, but about anything. How to be assertive and skeptical, and how to question things and not just believe everything you hear, and how to tell truths from falsehoods. And it's a very important skill these days. There's all this noise and people claiming things to be right, claiming all sorts of things to be true that aren't true. And so very important video right there. Don't deceive yourself before you even try to not deceive anybody else. Just don't even do it to yourself. And it's easy to do. It's easy to deceive yourself. Very easy. Anyway, so that's another great video I want you to read. On the website, the ones that are required are highlighted in red font. And then you can do other things that pick and choose from the rest. So this is another good one, the Coding in Ancient Computer. That's the one I talked about earlier, Antikythera. And then Alan Turing's Forgotten Ideas, the ones that are not as famous as the others. I want you to read that article too. And another great article by Scott Aronson of MIT called Who Can Name the Bigger Number? Again, mind-expanding kind of concepts that I want you to look at. So, and we talked about the imitation game. If you haven't seen it, see it. I'll give you extra credit for that. How's that? I wish my professors when I was a student would give me extra credit for watching cool movies, but my gift to you. So don't pass up on these opportunities. You'll come out smarter for it on the other end. So another handout that I want you to look at, and most of these kind of handout about discrete math and basic concepts of notation you would have seen before. What's a set, what's set membership, what's union, what's intersection. It's part of discrete math. Hopefully most of you have seen that before. But if you haven't, or if you want to brush up on all these definitions, there's a nice 10-page handout that I wrote. It kind of summarizes all the basic concepts of what's a graph, and what's a countable set, and what's an uncountable set, asymptotic notation, and big O, and omega, and little o, and all that stuff. So that's all in a single place, so read that one. If you know it, that's fine. Just look at it and tell me that you know it all, and I'll still give you credit for it. but you'll probably learn a few things that you didn't know when you look at that. Definitions are very important, basic concepts. It's one of my favorite cartoons about definitions. Galileo is trying to explain, or I guess Kepler in this case, is trying to explain to his colleagues, he says, so, the orbit of a planet is elliptical. He discovered that. And he's taking for granted that they even know the definition. So one of them is thinking, oh, what's an orbit? And the second one is, what's a planet? And the third one is, what's elliptical? And he's having a tough day with his colleagues there. Never mind that they probably frowned upon that very notion that there are other planets besides ourselves. Turns out that a third of Americans believe that the lunar landing was fake in 1969. Apollo 11 never reached the moon. How many heard that fake moon landing conspiracy theory? That's pretty bizarre. I mean, that's it's understandable why people can debate about their favorite deity versus other deities or whether deities even exist. It's all very kind of wishy-washy and nebulous and a matter of opinion and belief. But the lunar landing never happened. It's like saying UVA doesn't exist, but here we are. So that's pretty bizarre. So don't be one of those people. And I'm giving you a lot of ammunition in these talks and videos and web pages where you can go through them, and I'm giving you a lot of ammunition to not be one of these people going through life, believing in hokey, bizarre things, and not questioning what you're told, and try to teach you to think like scientists, and look at the facts, and examine them, and question them, and not just believe something because somebody in authority told you it's true. That's not good enough reason to believe something, whether it's a politician, or your friend, or your parents, or a priest, or a president. You need to question things and look for corroborating evidence and think for yourself. And I want you to encourage you to do that. And it'll also make you a better problem solver. It'll make you a better programmer, a better computer scientist, as well as a more informed citizen. That'll be bonus.
Professor?
Yeah.
One question.
Yeah.
Would we have to turn on write-ups for this thing as well?
Yeah, and he's asking, do we have to turn in write-ups? Yeah, just so I know that you looked at it. So all I'm asking is for a couple of paragraphs, nothing major, nothing that will take more than a few minutes to jot down and submit. For a book, make it a couple of pages, because a book is more substantial and there's more things to say. But again, I'm not asking you to spend a lot of time on writing it up. Just convince me that you looked at it, tell me what was interesting, new, surprising, what you learned. And if you didn't learn anything from that, it'd be interesting for me to know that too. But chances are you'll have stuff to learn from each and everything that I give you, because I tend to pick stuff that's cool and interesting and off the beaten path and has new twists on old topics. Right? So the centrifuge problem was one of those things that in a minute you'll see why. And most of these things have that property. They're cool, they're interesting, they're unusual ways of looking or thinking about things. And it'll make you better problem solvers, better algorithm designers, better computer scientists. And just better scientists. The word computer scientist has two words, computer and scientist. Guess which word is more important than the other? Computer or scientist? Scientist. So before you're a computer scientist, you are first and foremost scientist. That's what you're learning and training and hoping to be if you didn't know already. The fact that he's a scientist having to do with computers, that's secondary. The fact that you're a scientist is primary and much more important. Any questions about that? So I tend to harp on the more important word of the two, computer scientist. And don't get me wrong, you're going to learn a lot about computers and algorithms, and that's very important. But you're a scientist first and foremost. So that book is also required. There's another book called Infinity in the Mind, really, really cool stuff about magnitude of infinity. Turns out not all infinities are created equal. Some are bigger than others. How many knew that? There's lots of types of infinities. They're all infinite, but some are still provably bigger than others, mathematically provably bigger than others. And that book will tell you about that. Gerald Escher-Bach, that won a Pulitzer Prize back in '79. Don't let the dates fool you. It's a very, very insightful book all the way to the present. It didn't age at all. It's very fundamental stuff, insights, relating the works of Gödel and Escher and Bach, the artist, the logician, and the musician. How many have read that book or heard about that book or seen that book? Here's your chance to read it for fun and extra credit. Carl Sagan, The Demon Hunter's World. I want you to read that. Again, it's like the skeptic analog. It'll teach you how to think more incisively and skeptically, and how to dig into facts and corroborate them and make sure everything makes sense and not just fall into weird beliefs simply because somebody in authority told you that you should believe that. It'll help you avoid con artists in your life, no matter at what level they're coming at you. This one is just fun. What if it's the guy who does the XCKD cartoon or whatever it is, and he expanded it into an interesting set of observations about science and kind of cool questions that he's answering. And it's really, really fun reading. So, at least 2 per week, at most 2 per day. That will help you pace it. And I'm just asking you to not cram, basically, with under those rules. Any questions about that? All right. So, there's lots and lots of other papers on there. I'm just flashing a few more. Again, don't let the dates fool you. Some of them are 15 years old or 20 years old, but they're very, very insightful. And I picked ones that don't age very much. There's always more follow-up work, and some, but they still have the basic principles and the insights. And a lot of them come from Scientific American, and they have beautiful color photographs and diagrams and illustrations and really, really cool stuff. So this is more on the extra credit side. If you want to do more, lots of topics. It's all on the website. Everything is posted there. Everything's available instantly on the class website. For example, this paper by David Patterson, written in 1995, and he's talking about microprocessors in 2020, and we're right now in almost 2020. It's interesting to see retrospectively what the guy who invented RAID and RISC, that's the guy, David Patterson, thought about where computers will be in 25 years. And so you can read that with kind of a retro-forward kind of mindset and see how the present, roughly 2020, compares to his prediction of 25 years in the future from the vantage point of 1995. So a lot of these papers have kind of meta lessons in them too, interestingly. So again, this guy invented RISC and RAID, among many other things. He's one of the foremost computer architects in the world. How many know of him, right, or read a book by him in the architecture book? Usually you study from his book. Okay, so again, lots of topics, very diverse. Some of them are wiki pages. I'm giving you lots of credit and opportunity to do well in the class and just enlighten yourself and wrap your mind around lots of interesting, cool topics. Okay, any other issues or questions? What I'm trying to accomplish here with you, to make you better problem solvers and just better scientists.
Have you read all of them yourselves?
Yeah, I read most of them, yeah. Good question. He's asking if I actually look at, yeah, I wouldn't put something up there that I haven't read myself, because otherwise, that could create all sorts of issues, right? If I don't know what's in it, I wouldn't recommend it. All right, so ask questions as soon as possible. Don't fall behind. Don't cram. Solve lots of problems. That's basically the strategy in a course like this. It's very general. Typical, archetypical, problem solver. We used to have MacGyver back in the 70s and 80s. Now we got Matt Damon on Mars. The Martian. So basically, The Martian is like MacGyver in space. How many have seen The Martian? Beautiful movie. Focuses on problem solving, resourcefulness, being resourceful. Right? He basically survives on Mars for a couple of years, just being, with a sack of potatoes and his wits. Amazing story, and scientifically very sound. Actually, the guy who wrote this movie and the book before the movie did his homework really, really well about the actual conditions up there, what's possible, what's not possible. Just a beautiful, it's beautiful to watch people doing high-level, clever, insightful, deep problem solving. It's just it's entertaining as well as it improves you. So back to this problem. How many have a solution? Speaking of problem solving, you have a centrifuge, 12 holes. Can you or can you not spin 5 without it being out of balance? How many say you can't do it? All right, we got some votes. How many say you can do it? All right, we got some other votes. So interesting, we have a split vote. So anytime a room full of smart students like yourselves have a split vote on a yes/no question, by definition, it's a good question, right? Otherwise, you'll all be agreeing and hopefully have a correct answer. How many can prove either a yes or a no? Not just suspect that it's true, but I can actually argue or prove it mathematically. Okay, a lot less people. Any thoughts? First of all, let me not be presumptuous. Any questions about this question? Anything unclear about what we're doing? Okay. All right, let's throw around some ideas. Yeah.
All the material within the test tubes are equal?
Yes, all the materials inside the test tube are equal, uniform, equal mass, equal density, equal size, equal shape. They're indistinguishable. So there's no dirty tricks here. Good question. Yeah.
How do we define balance?
That's an excellent question. It says, how do we define balance? How many wondered about that on your way to a solution? If you didn't wonder about that, then what are you trying to solve exactly? I ask you to do it in a balanced way, and you never stop to question what balance means. Then how do you know if you get there or achieve it? Very insightful question.
But you already said if they're not balanced, then it will start fumbling and it will
Yeah,
start.
if it's not balanced, it will start fumbling.
Yeah,
But
that's-
why? What is balance that will cause it to fumble and not spin equally, stably along its axis without any vibration? Yeah.
A geometrically centered center of mass.
Yeah, so he's saying balance is when the center of rotation and the center of mass do what? Coincide. Because they don't have to coincide. The center of rotation could be this, but the center of mass could be here. And so the center of mass is moving around the center of rotation. And by the way, what is center of mass? It's a definition of the center of mass of an object. I heard somebody whisper vectors. Anybody? Yeah.
So for center of mass, if you support the thing at the center of mass, it will not fall.
Yeah, it will not move or fall or tilt or veer off. There will be no net force. Right? Now, how many get that? So yeah, you can do it with vectors. Or you can do it more intuitively if the object is simple enough. Right? If you have a disk, the center of mass is in the center of the disk. If you have a square, same thing. If you have a sphere, three-dimensional, it's in the center of the sphere. But the center of mass and the center of rotation of an object are not necessarily the same thing. But when they are, it's balanced. When they're not, it's unbalanced. So think about what just happened. I asked you to solve a problem, how to do something in a balanced way, and all of you rush to do it or not do it, and only a few people, like you, question the definition. Ask, what does that even mean for something to be balanced? So let that be a meta lesson to you. Always know what you're talking about when you speak or try to solve a problem. Know what the terms mean. Don't throw around terms without definitions that you don't even know what the definitions are. Then whatever else comes in the heels of that is nonsense. How many see the point here? Okay. Make that an active problem-solving heuristic or rule. Always know the definitions of all the words that comprise the problem. Otherwise, you have no idea what you're trying to solve. And amazingly in life, a lot of people are going around throwing all sorts of words that they don't even themselves know what they mean, and yet they expect you to understand it. And they don't even understand it themselves. And then they argue with you over it. And in extreme cases, they're willing to commit violence over it. And some of these situations occur in religious contexts. So, and you may know some of these people. Some of them may be related to you. I'm not being derogatory, I'm just stating the obvious. But keep that in mind. So now we know what balance means. So now we have a better chance of solving it. When before you knew what balance means, you didn't have a chance, really. So that's the first question we want to ask, is what each word means, what each concept or premise means in the context of the problem. Before we even rush ahead and try to reason about things that we don't know what they mean, it's almost futile. All right, so we can balance two, right? Here the center of mass is the center of the rotation, no problem, then that's balanced. You can balance three, like equilateral triangle vertices, put three test tubes there, and we can do it. But can we balance five still? How many say we can balance five? How many say we can't balance five? Still a split vote. A few people are voting each way. think more people are saying we can balance 5 if it's shifted. All right, any other thoughts? Ideas, suggestions, strategies? Yeah.
I think if you superimpose if you just put the red ones across where the blue ones are, it'll keep the center of mass the same.
Okay, he's saying if you superpose these two configurations, both of which are balanced, the superposition of the two, putting them on top of each other, will also be balanced. So he's basically saying that we can superpose them together. And if we superpose them together, you get this configuration. You want to see it again in slow motion? Here we go. Instant replay. Yes. Superpose. And he's saying basically that superposition is also balanced because the two components that you used to create that superposition were themselves balanced. How many buy that principle or notion? Believe it. How many believe it? How many don't believe it? Okay, we have skeptics. That's okay. So you're doing what I actually instructed you to do. You're skeptical about it. Let's try to resolve that one way or the other. Could somebody argue more rigorously that if you have two balanced configurations, the superposition of them, assuming that you coincide the centers of rotation of both, must also be balanced? How would you argue that? Somebody mentioned vectors earlier. How would you argue that using vectors? And by the way, you don't need vectors to argue that. But let's use vectors to argue that. And then let's not use vectors to argue the same thing.
So the center of mass actually is the individual masses times the coordinates of mass. And it's the sum of all the individual masses divided by total mass.
Yeah. So the center of mass here is these two vectors, one pointing from the center to here, one pointing from the center to the other red dot. And these two vectors obviously are equal but in opposite directions, and they balance, they add up to 0. Right? How many agree with that? Okay. These three vectors here add up to 0 also. The vector from the center to this blue dot, and to the third blue dot, all these three vectors also add up to 0. How many believe that? Yeah. So if two vectors add up to 0 and three other vectors also add up to 0, now you throw all 5 vectors into the same bag, what will they add up to? 0. Because addition is commutative and associative, and it doesn't matter which way you add them up. You have two quantities that are 0, adding them up together in a linear fashion will also get you 0. It has no choice. How many see that? So it's 0 for these 5 vectors. And if it's 0 for these 5 vectors, the center of mass is right smack in the middle, which is also the center of rotation. And that's the very definition of balance you just said a minute ago. So these 5 test tubes in this configuration will be balanced. End of story. Well, it's not the end of the story. It's end of first chapter of the story. There's more. But how many believe it so far? Okay, so we argue in terms of vectors. Here's a way to argue it more intuitively. Let's say you have this configuration of 2 along a long axis, and it's just spinning around on a long axis, like a bicycle wheel, with 2 weights on opposite sides like this, where the 2 red dots are, and it's spinning on an axle really fast, and you're holding the axle, and it's not vibrating because it's balanced. And then you have a separate axle where you're spinning 3 of them equally spaced along the rim of a bicycle wheel, like tennis balls or whatever, and that's balanced because that by itself is balanced. And both of these axles are not moving anywhere. This thing is just spinning in a balanced way on top of them. How many can imagine this scenario? Okay, it's not hard. Right? And then you bring the 2 axles together and you touch them. Nothing will start vibrating because both axles are motionless, not vibrating. One of them has a pair rotating, one has a triplet rotating in these 2 configurations respectively. Now you're connecting the axles. Neither one of them went anywhere, so by touching, they're not going to go anywhere either. How many can see that? And then you bring the 2 bicycle wheels along this combined axle together closer and closer and closer, and nothing will change either until they touch. And nothing will change either. It'll remain balanced in this thought experiment. How many can see it, visualize it, think about it? So 5 will be balanced in this kind of thought experiment. Now, this thought experiment is an intuition. It's not a rigorous proof. The one with the vectors is more rigorous. And when I showed this to one of my colleagues years ago, who was a biologist, and he had centrifuges in his lab, he didn't believe it either. So don't feel bad. A 30-year-long research, superstar researcher didn't think that 5 could be balanced either, and he's running centrifuges every day in his lab, in his biology lab. And he didn't believe that. And he didn't believe my explanation about vectors or this intuition about axons and none of that. He said, I still don't believe it. So what do you think we did next? I was in his office. His lab was next door. I said, let's do it empirically. Let's run a test. So we went over to his lab, and there's this, $50,000 centrifuge. And why do they cost so much, by the way? Why does the centrifuge, it's only a cubic foot, cost $50,000 or $20,000? It's huge amount of money for something that small. There's a reason for that. If the centrifuge, if the rotating part was made of steel, and you spin it at 60,000 RPM, that's 1,000 revolutions per second, not 1,000 per minute, 1,000 per second, the G-force is so large, it'll deform the steel. There's only one material it can be made of, so it doesn't just deform and fly apart. Because if that centrifuge fails while it's spinning at 1,000 revolutions per second, guess what would happen? It's called an explosion. Right? You're going to have shrapnel flying supersonically off the hub. That's an explosion. Okay, so you can't have any failure, and steel is not strong enough. So what does it have to be made of? Diamonds? That's a good one. Diamonds are hard, but they're not necessarily strong. There's a difference between hardness and strength. Actually, if you take a diamond and hit it with a hammer, it'll shatter. So it's not that strong, but it is very, very hard. It'll scratch any other material. Titanium, yeah. And that's why it costs so much, because it's a big block of titanium. It's a very expensive metal, much more expensive than steel. But I digress. We ran the experiment. He said to his postdoc, okay, fill 5 test tubes. Professor Robbins says this will work. I don't believe it, but put it in these 5 holes around the center and rev it up, but not too much, because we don't want to damage this expensive, piece of equipment that we paid $50,000 for. And we don't want any accidents either, kind of more important. These postdocs dutifully filled up these 5 test tubes, identical size, with pure water, same density, same size, same weight, and put it in these 5 positions and start cracking it up. And it wasn't vibrating. And then crack it up some more, it wasn't vibrating. And finally he says, okay, now take it to higher speed, still balanced. Finally, full speed, perfectly balanced. So the researcher tells me, he says, now I believe you. So, that's the difference between experimentalists and the theorists, right? The theorist knows it's true. Experimentalist has to see it and then believe it. That's okay. We need both kinds of mindsets in science. And ideally, the two should agree. In other words, what you think should be true, the experimentalist should verify that if that's the case, it is true. And vice versa. What the experimentalist observes to be true, the theorist should have some good mathematical, scientific explanation to why it's true. And the two come hand in hand and reinforce each other, and that's called science. Okay. But I thought it was kind of amusing that he was much more convinced by the postdoc experiment than my explanation. But eventually he saw both, right? Not just one. And I knew that the centrifuge is not going to go anywhere, because this kind of reasoning is very, very sound. The reason, the superposition is a very strong principle. In physics, it happens all the time. Right? The parabola is a superposition of a linear motion and a quadratic motion. How many know what I'm talking about? So linearly, it moves this way, but vertically, it moves in a square fashion, inverse square law. It's gravity. That creates a parabolic motion. And linearity is a very basic concept. In mathematics, linear algebra, linearity is often expressed as a function applied to a sum is the sum of the function applied to both parts separately. And x and y can be arbitrary thing. And when this is true, your function is linear. Right? How many understand that? And gravity and other forces work this way. in physics, when you have a bunch of forces acting, the resulting motion of the object with all these forces acting is the linear combination of all the forces. The linear combination. Not a non-linear combination, or quadratic or cubic or square root combination or geometric mean combination. It's the linear combination of all the forces. Very basic principle, mostly math and physics. So now let me ask you another question. Can you spin 7 test tubes? How many say yes? Okay, that's better. How many say no? But you got it all correct. Everybody's correct now. Why? Why can you spin 7? What's that? Because 4 and 3 could be superposed. And that's a good reason. And it's correct. Give me another reason.
You just reverse that.
Yeah, negate the holes and the non-holes in this 5, and you get 7. So spinning 5 masses is the same as spinning 7 holes, conceptually and mathematically. If you think about these 7 holes as negative masses, in reality there's no such thing as a negative mass. Actually, there is, but never mind that. Mostly there isn't. But you can think about it mathematically in terms of vectors. These holes are vectors pointing in the other opposite direction. So mathematically, holes and masses are interchangeable. Just reverse the sign of the vectors. How many get that? Yeah. And if the first set add up to 0, the second set will add up to 0 too. When you reverse all the vectors. Or when you negate the vectors with the other vectors, you get a complementarity situation where you paint the holes with masses and you make holes where the other masses used to be. And this 7 must balance too. Because it's a complement of the first thing that balanced. So the complement of a balanced configuration must also be a balanced configuration. Because the sum of the vectors must add up to 0, and some subset add up to 0, so the rest must also be 0. How many get that? And you only knew the answer for the 7 all of a sudden, because you applied the same principle, superposition. But looking at it differently, complementarity gives you the same answer. The answer being yes to whether it's balanced. But you also have to be careful when you apply superposition, because what if we carry it further? So now we know 7 is balanced. And we know that 4 balanced. 4 is balanced. Right? 4 is like a 2 plus a 2. So 7 is balanced and 4 is balanced. So 7 plus 4 superposed must be balanced too. But 7 plus 4 is 11. Can you balance 11 test tubes? How many say yes? Because it's 7 plus 4. How many say yeah, you can balance 11? How many say no, you can't balance 11? Ah, yes, my Padawans. I'm proud of you. Why can't you balance 11? Because you can't balance 1. And 1 is the complement of 11 with respect to the 12 hole. So you have to be careful not to apply a principle beyond its breaking point either. So yeah, superposition works as long as they don't begin to overlap because of geometric constraints in the configuration. And if you think about it more carefully, you'll see that there's no way to superpose 7 and 4 without some conflicts. 2 things will end up in the same hole. 2 test tubes will try to occupy the same hole. That's no good. So you have to be careful and be insightful and not apply principles beyond their breaking point. But that's okay. Both are still very insightful. Superposition is a very important insightful principle here, and so is complementarity. And the two better agree. Okay. So we already talked about the empirical testing. And by the way, let me give you an insight as to why 3 must be balanced. We already know from vectors that 3 must be balanced because 3 vectors pointing in these 3 directions will add up to 0. You can do the math, the sines and the cosines will get ugly, but they'll all cancel out. How many get that explanation? Let me give you another explanation. It's much more intuitive why this must be balanced. Let's say you balance these 3, and we're not sure if it's balanced or not, but the claim is that if it has rotational symmetry, if it has a non-trivial rotational symmetry, it must be balanced. And if you rotate it a little bit and it looks exactly like before you started rotating it, it must be balanced. assuming the rotation is not 360 degrees, it's some smaller angle. How many agree with that statement? This has that property. You rotate that 180 degrees, and it looks the same as before, and the claim is that's balanced because of that. It's a sufficient condition for balance, not a necessary condition, because this has no rotational symmetry. The 5 has no rotational symmetry other than 360. How many understand that? So rotational symmetry is not the criteria for balance. It's not a necessary criteria for balance, but it is a sufficient criteria. If it's rotationally symmetric, it is balanced. If it's balanced, it's not necessarily symmetrically, rotationally symmetrically. So here you have 120 degree rotational symmetry among the three. 120 degrees or 240 degrees looks the same. Why is it balanced? Well, show it to some very, very smart person, an oracle, a deity, omniscient. Show them that configuration and they say, okay. Have them walk out of the room, and then you either rotate it 120 degrees or you don't. But let's say you rotate it 120 degrees, and then come back into the room and look at the rotated version. Omniscient though they are, they have no way of knowing if it's rotated from the original or not, because it looks the same. How many get that? You may have rotated 120 or you may have left it alone. They have no way of knowing. So the two are equivalent. And let's say this 3, you ask them, is it balanced? And if they said, no, it's not balanced, and you rotated 120 degrees and they came back and they couldn't tell if it's rotated or not, they can't possibly change their answer. Otherwise they'd be wrong, but they're omniscient. So they can't be wrong when they have all the facts, and they're looking at all the facts of the case. So they have no way of telling the difference when it's rotated non-trivially or not. And because of that, if they said this is balanced, any rotation of it would be balanced. And if they said this wasn't balanced, any rotation of it wouldn't be balanced either. And if you think about that enough, you'll see that that's sufficient reason for it to be balanced, because it has to be consistent. Right? Because if this wasn't balanced, the center of mass would not coincide with the center. So the center of mass might be right there, where the green dot is. Right? So have them walk out the door and have them come back and actually rotate it. Right? Ask them where the center of mass is, and they'll say it's not in the center, it's like right here. Why is that wrong? Because if you send them out the door, rotate it 120 degrees, and brought them back in, it looks to them the same as before, so they have to say the center of mass is exactly where they said it was before, namely right there. But the center of mass is no longer there because it was rotated 120 degrees, it's a rigid configuration. Now the center of mass has rotated 120 degrees with it, now it's over here. But this poor deity can't know that, even though they're omniscient. Which means the center of mass must be at a place where if you rotate this 120 degrees, it cannot change position. Because this deity must be right. It's omniscient. There's only one place in this whole circle where if you rotate it 120 degrees, that dot will not change position. And where is that place? Right in the center. It's the only place. It's a unique position for that center to be, for the center of mass to be. So the center of mass of these 3 dots, 3 blue dots, is the center. It has no choice. And I can convince you of this without using sines, cosines, vectors, or anything else. The real numbers are square roots of 2 or square roots of 3 over 3. And that's why a symmetric configuration must be balanced without using vectors. How many understand this argument? Okay, that's a more intuitive argument. So another meta lesson here is many ways to prove something. And some ways are better than others. Using vectors is okay, you'd be correct. But using superposition, it won't just be correct, you'll be elegant too and impressive. And it generalizes. Because if you use vectors, you can do all the sines and cosines and square roots of 2s and 3s and add up to 0 and show that this 5 is balanced. But if you want to try to balance next 7, You have to start from scratch and find another set of vectors, and now it's even harder because the angles are weird. And that solution is correct, but it's not easily generalizable. The one with the superposition is much easier to generalize. If I ask you the question of if you have a centrifuge with 360 holes, not 12, 360 holes, very large centrifuge, which configurations are balanced? 2? How many say yes? 2 test tubes on a 360 hole centrifuge, you can balance 2 test tubes? Yeah, of course. 3? Yeah. 4? Yeah. 5? How many say yes? Yeah. 6? Sure. 7? Yeah. 8, 9, 10, 11, 12, 13. All these are doable now. And now you have solutions to much, much bigger problems without using vectors. And good luck to you try to use vectors. If I ask you, can you balance 123 test tubes on a 360 hole centrifuge? Yeah, you can do that with vectors. And we'll see you next week when you're done. And the proof won't be very believable, even though it'll be correct. So there's elegant ways of proving things and arguing things, and there's not so elegant ways, and elegant is better. So in this course, another meta goal would be not just to be correct and right, but to be elegant and convincing and intuitive and beautiful while you're being correct and right. We're going to take it to the next level, kick it up a couple of notches. Arguments, proofs, scientific insights. So notice that we solve this without any vectors, without any calculus, no sines, no cosines, no equations even at all, whatsoever. And the truth is guaranteed. It's obvious that it's correct. There's no question about it. You can wrap your mind very tightly around the truth and correctness of these arguments. And we expose the fundamental principles here. The symmetry, superposition, the linearity, and the complementarity. So we came up with 4 different principles that are now allows us to solve much bigger problems, more complicated instances of the same kind of scenario. And that's a good day in logic and math and problem solving. I'm not saying every problem could be solved that easily, that insightfully, that generalizability kind of banner of solution. Self-driving cars can. There's a lot of ugly boundary cases, millions of them. That's why we don't have them yet, but soon we will. And try to go for all these other bonus properties when you solve problems. Generalizability and fundamental principles, and try to get some insights. And on a good day, it'll also be elegant and beautiful. And that's a plus. Okay? So, also, we don't want to use induction unnecessarily. And I'll talk more about that next time. But anyway, that's probably enough for one day. Any questions or comments? If somebody wants to add the course, just give me a course add form. I'll sign it, but pick it up for me right now and submit it to the CS office. I'll sign it for you, but you gotta submit it. Any other questions? So by next Monday, 2 things will be due, and I want you to watch the time management lecture first, because that's really important. It'll help you with all the rest. All right, see you next
Yeah, I mean, like, his slides are like really similar. I can tell you that they're like, so I know college struggles with a lot of stuff like Chomsky and stuff like that. Yeah, that's all the stuff. that none of that is covered here. You've taken undergraduate algebra, right? If anything, there's going to be more removal of that, with the only exception being that